Welcome back. The first of the reactions that we are going to look at is when a compound containing a double bond reacts with mercury 2 acetate in presence of tetrahydrofuran and sodium borohydride. If any of those names sounds alien to you or you've never heard of them, it would make sense because some of these are very much compounds you would observe in an organic chemistry class. So let's look at an example. Okay, I mentioned several things. Okay, first of them is mercury 2 acetate. Now you may not have heard this in usage in your general chemistry class, but you probably have learned how to write formulas given a name, and mercury 2 acetate is Hg and OAC2. Now OAC is nothing but acetate. Okay, that's just the chemical observation of it. You do not have to memorize any of this. Okay, acetate. It's also known as, it's written, if you're familiar with this, this is also is known as an acetate group. Okay, so an HgOAC2 can also be written as HgCH3COO twice. As I said, you do not have to memorize this. So this is the major ingredient that we are going to combine with our double bond and make alcohol. Okay, so mercury 2 acetate, and the second thing I said is THF. Okay, it's called tetrahydrofuran. Okay, this is an excellent solvent. It's an organic solvent. It's commonly used in many organic reactions. And the third thing I said is sodium borohydride. These are the major components that we are going to use in the formation of the alcohol. So these are basically your chemical reactants that would react with your compound containing the double bond. Now this is an excellent reducing agent. Okay, in an organic chemistry, a reducing agent is simply supplies hydrogen. Okay, just think of it that this particular compound right here is an excellent source of hydrogen. So the compound that it reacts with, if it needs hydrogen, there is no better reagent that you would sort out to than sodium borohydride. It's an excellent reducing agent, means it's got the remarkable ability to supply hydrogen to a compound when it's in need of hydrogen. Okay, tetrahydrofuran is a solvent because if you remember, like dissolves like. Most organic compounds are not soluble in water. Okay, only aqueous compounds tend to be soluble in water. That is, compounds that can dissolve in water. That's why we say like dissolves like. Most organic compounds are nonpolar, means they require nonpolar solvents to dissolve them for the reactions to be carried out, and that's why we use tetrahydrofuran. We've also used dichloromethane and other solvents. Okay, so tetrahydrofuran is a solvent, and this is the actual reacting species, which is the mercury 2 acetate, which reacts with our compound containing the double bond. All right, so what is the actual reaction? Let's look at an example. Okay, so say this is my compound containing a double bond and say a methyl group. Okay, so far everybody is with me because these are things you're familiar with based on some of the things we have done. All right, so let's say it reacts with mercury 2 acetate. Okay, and then what's the net reaction? This is how organic people typically write stuff. Okay, they write all of the reacting reagents that you need, and then the starting material and the product. Okay, Now keep in mind, this already you have a nitrogen here. Now this has a very, very stark resemblance to your, this is a Markovnikov product. What does that mean? Well, basically, if you look at the mechanism, okay, or even before we look at the mechanism, the OH group, which is your hydroxy group, gets added to the side that contains least hydrogen, and the hydrogen gets added to the side contains already more hydrogen. So if you compare these two groups where the double bond is actually present, this group actually contains no hydrogen, this contains the hydrogen. So I'm going to circle what is that we've actually added to the existing molecule. So these are the two things we have added, in fact. And the OH group goes to the carbon that contains least number of hydrogen, and the hydrogen goes to the carbon with more number of hydrogens, right? Okay, so let's go back and look at the actual mechanism. If you remember, this is starkly very, very, very similar to when we looked at our bromohydrine formation, okay, or bromonium ion formation, sorry. So say if this is your starting material, okay, okay, this reacts with, I am going to, instead of writing it this way, I'm going to write it this way. This is essentially what it looks like, you know, this HGOAC, this is what it looks like. And this is very similar to our BR that we have learned. Exactly same. Two things that are identical are connected by a single bond, right? Now, if we actually go get a different color, we can go through the mechanism. Now, as I said, the mechanism may not be necessarily important from a pre-professional exam preparation because outside of an organic chemistry class, the mechanism is rarely tested. However, if you remember the mechanism, the chemistry seems to make more sense, okay? So I'm not telling you to memorize any of the mechanisms, because sometimes I think just knowing what the product is sufficient from a pre-professional exam perspective, right? Or even just from a organic chemistry preparation perspective, okay? So this double bond gets used up to make a bridge to this mercury, and if you remember, the oxygen's got lone pair of electrons, so one of them comes back and attacks this carbon right here, and in the process, this gets cleaved, okay? Let's go get. Now, what does that mean? Well, this is our intermediate, okay? So I'm going to put that in brackets, okay? That means there's a bond made between this carbon and this mercury OAC. Because something is lost an electron, it gets a positive charge, and then this is connected back. And then we still have our hydrogen here. And what is come off is whenever a bond gets transferred to another element, it gains negative charge. Whenever a bond or electron is lost from an element, it gains a positive charge. And this is something I have repeatedly said when I made earlier videos. Okay. Now what happens? Let's go get another color so we can actually wrap this up. Now, if you remember, you got to use every reagent that is up there. The THF is the only thing that's not used up because it's just a solvent. Okay, it's where everything is carried out. So we have already used this. Now we have to use the water, right? So let's go get the water. What happens here is, keep in mind, again, some of us just forget the general chemistry ideas. That's why it's always say general chemistry 1 and 2 is such an important coursework. Now, this is something you probably learned where you develop Lewis structures. And so that's exactly the same thing. So this reacts with your, and it attacks this carbon containing, actually, sorry, let me step back. Okay, this attacks this right here. Okay. Okay. And what happens here is now we do know carbon cannot have 5 bonds, right? Now, if you remember that bromonium ion thing I've explained, the lone pair of electron is used as a bond. So by the time you finish, you will have 5 bonds, and that's not good. So that means this bond gets broken and the electron is given back to the mercury acetate ion, right? So what happens in the process is, let's go get another color. Okay, so I'm just going to put the arrow because there's not enough space here. Okay, so you have your CH3 and then you have your OH. Let me ask you a pop quiz right here. Is there something missing on this oxygen or anywhere in this vicinity of things? Well, because this oxygen is used its lone pair of electrons to make a bond, the oxygen should get a positive charge. As I said, anytime a bond or electron is lost, chances are you're going to have, so this is what you're left with. Okay. Again, this is unstable because anytime in chemistry you have an ion that is positive or negatively charged, it would try to get out of that as quickly as possible. So what does that mean? Let's go get another color. Well, another thing people forget is just because there's one water written here, that doesn't mean there's only one drop of water or only one molecule of water. There's probably plenty more water out there. So what's going to happen here is this hydrogen would react with this lone pair, okay? Because this is an unstable situation, okay? So what happens in the process is you're going to end up with OH because the hydrogen is gone. Okay, this is essentially same as you basically this bond leaving and the positive charge neutralizes itself. That means there is no more positive charge, but you also notice you don't have that extra hydrogen. And then now you have your, this is still not over, okay? Okay, this is still not over. Thus we've used this and this. As I said, we will never use this as this is just a solvent, but we still have to use this. What did I say earlier about sodium bromohydride? They are reducing agents. So whenever a molecule is in demand of, now keep in mind, this is an acetate ion, right? So this would look like this, right? It's negative. So not only this molecule needs an hydrogen, when this whole thing comes off of this molecule, it also badly needs hydrogen, and there is nothing better to supply those hydrogens other than sodium borohydride. So when this reacts with the sodium borohydride, it adds that extra hydrogen here, and then the HgOAc combines with another hydrogen. Okay. Now, if you notice, the point of the matter is we have now the correct product, and that's exactly what. If you noticed, I went back and changed my arrow here, right? Because this, if this had attacked here, then we would have had the anti-Markovnikov's product, right? But what do we need? We need Markovnikov's product, right? That means it must attack here. So the rule of thumb here is when you want a Markovnikov's product that corresponds to an alcohol, so as I said, the OH by itself is known as hydroxy, but when it is part of a compound, it's known as an alcohol, right? So right now, we have attached the OH to the carbon containing the least number of hydrogen, and the hydrogen went to the compound containing more number of hydrogen, and this, folks, right here is the actual mechanism for it. Okay, so in the next video, we are going to look at boration. So this is mercury acetate reaction. And then the next one, we are going to look at same double bond, what happens when it reacts with borohydride. All right, so stay tuned.